You remember the other day when we did ellipses, and I gave you the definition, the set of points, da-da-da-da-da. And we drew with the string. Do you remember what that definition said about what happens? Yeah. The distances, you pick a point on the ellipse, and if you measure the distances from both sides, the sum is always going to be the same number. Okay, on a hyperbola, it's the same thing. If you pick a point on a hyperbola and you measure the distances from each focus, and you subtract those differences, it's always the same. So ellipses were when you added the distances. Hyperbolas are when you subtract those two distances. So it's the exact same thing as your ellipse definition. It's just that it has the word difference in it instead of sum. So the set of points in which the difference of the distances from the two given points is constant. You know, if you read that definition, just read it and had to try to figure it out, it doesn't make a whole lot of sense till you see it in picture form. Now, I can actually show you that a little better. Are we still writing? Okay, we'll pause a second. Okay, so to kind of give you a visual on that one, if you're actually, this does it nicely, it's measuring length 1 and length 2 down here, and then showing that when it subtracts it, the difference in those two purple lines is 4. And if I pull that out here to a different point, yeah, the distances change, but when I subtract them, it's still 4. And if I move that point clear over onto the other branch of the hyperbola, the difference is still 4. It stays 4 every single time. So it doesn't matter where you're at. This particular problem always has a distance of 4. Somebody last block said, well, do they always? They always have 4 as the difference. No. It could be, the difference might be 6, 8, 10, whatever. So that can vary. Okay. The other thing you're going to have to know about hyperbolas, you get to learn a new word. You get to learn about what asymptotes are. It's spelled right there. I'll write it bigger in a minute, but asymptotes, I'm going to turn the asymptotes on. When we graph it by hand, we have to have the asymptotes. You'll notice the asymptotes are these dotted lines. Where do they cross each other? They have to cross at the center. And they extend outward. What do the curves do as the curves extend outward? The curves are getting closer and closer and closer to the asymptotes. Asymptotes are not only used in hyperbolas, we're actually going to hit asymptotes several more times this year on different graphs. Asymptotes form a boundary line. This curve will never cross the asymptote. In fact, theoretically, it never touches the asymptote. If you could reach infinity, it would touch the asymptote. But those lines, so as you extend a hyperbola out, it virtually becomes a straight line because it keeps getting closer and closer to the asymptote. So for us, the asymptotes are going to form the boundary so we don't make our curves go too wide. So asymptotes are actually really cool. Now let me switch on you. So you probably want to know, because I believe you have a journal question about the purpose of asymptotes. So they form a boundary which the curves approach as they extend to infinity. Okay, if I write the infinity symbol, do you all know the infinity symbol? All right. Sideways 8 is usually... Yeah, now, we always have some issues. Like this year, my calc students just did it this week. They think you can't ever cross an asymptote. Your graph can cross an asymptote when you're on 0, 1, 2, normal numbers. Asymptotes are only the boundary they don't cross when you're extending toward infinity. You can cross an asymptote before that. Hyperbolas will not ever cross it. But some graphs can cross an asymptote. So that was exciting, right? Asymptote. I can tell you're a female audience. They usually giggle at that word. No. All right. So every conic section had reflective properties. Obviously, then a hyperbola must have reflective properties too. So I'll bet you all can halfway guess what's going to happen here. Now this one is a little strange when you do the hyperbola. You'll notice they only put one branch on here of the hyperbola. You have a focus. The other focus is over here, but the other branch is not in the way. Okay, when this one actually has a start button, and it formed a circle with this left-hand focus as the center, because what it's going to do is it's shooting, the red circle is going to shoot beams toward this focus on the left. They're going to shoot forward, they're going to hit the hyperbola, and where do you think they're going to go? They all were shooting toward the left-hand focus, but they hit the hyperbola and bounced the right-hand focus. And it doesn't matter, I can make this thing...
So they use hyperbolas for like dim lights then?
For what lights?
Like you said, high beam lights.
Oh, I don't know if they do it. Never thought about that. I actually don't know on that one. Okay, so that was a small hyperbola, but the focus was so close to the vertex you didn't hardly see it. It's kind of probably better if I make it go big, because now I'm making the focus get farther out. So if you shoot toward one focus, it bounces to the other focus. Now what's interesting, I wish this one doesn't do it. It works the same way if you're on the outside of the hyperbola. So if I was on the other side of this blue curve, and I was to start shooting toward the focus that's inside the curve, once I hit that branch, it's going to bounce me over here to the other focus. So whether you're shooting from the outside or shooting from the inside the curve, as long as you're aimed toward a focus, it will then bounce to the other focus every time, which is semi-amazing, actually. That really works. So let us draw a picture here for those out in video land. So I'm going to use this one, and I'm going to draw, so you can get that one below. If I am on the inside of the hyperbola, I'm shooting toward this focus over here, but I hit the branch of the hyperbola first. Where's it going to go? It's going to bounce to that other focus. But if I'm on the outside, and I'm shooting toward this focus, when I hit that outside branch, it's still going to bounce toward the other focus. So either way you go, you're going to bounce. So who cares? Hyperbolas are kind of weird and kind of hard to see a lot of real world uses for them. But there's kind of one of the most interesting characteristics. I'm sure you all have seen a lot of nuclear power plants. That was a screaming yes. We all visit them regularly. If you have ever seen them, even pictures of them, you may see they have steam that's released into these towers, but the towers aren't straight up and down. They curve inward. I didn't get mine curved very evenly. You might get a better curve. That's a little better. They curve inward. They're actually hyperbolas. They call it a hyperboloid because it's a three-dimensional hyperbola. The question is, why would they want to do that? Well, okay, what would they not want to get released into the air? Any of the nuclear radiation. So, they release steam below, they release steam into these cooling towers. But there might be some radioactive particles bouncing around. But, they can be bouncing around, but eventually, if one bounces toward a focus, bounces toward that focus, where's it going to bounce next? Bounce to the other focus, which is then going to bounce it to that one, and then what's eventually going to happen? It's going to get stuck right there going back and forth at the center. They can create a collection device at that point that collects all the radioactive particles that they go escape. Pretty cool. Pretty cool use of math. So, nuclear cooling towers are one of your uses. As with the other shapes I've already given you, they also use hyperbolic mirrors inside telescopes and microscopes. So that one's still going to be with us. Air hockey? Does it have a hyperbolic curve? Oh, it gets stuck back and forth? Well, if they have curves on it, then they can do that. It could be.
Whenever you hit it, it like goes back and forth.
Yeah, you're right, it does.
Maybe it does like that.
Okay. You may also never have noticed that if you have a lamp with like a lampshade, how does the light come out of the lampshade? You'll have a shadow coming up and a shadow coming out at the bottom. So the shadow coming out of a lampshade could be a hyperbola. So next time, tonight, you get a lamp turned on, look at the shadow. All right. So, okay, card time. Happy drawing here. You got to get these two babies on your card. My suggestion is draw the axis, draw the dotted asymptotes through there. Your curves just curve out and go toward the asymptotes. Just with like ellipses, a hyperbola has an A, a B, and a C. A will always be from the center over to the vertex. That's going to be A. B is weird. If you start at the vertex and you go up or down to the asymptote, that's B. And the good news is C is always the same. C is always center to focus. But C's on there twice. Yeah. The diagonal of that triangle will also be C. So look, it's a right triangle again. And what does the Pythagorean theorem say about this one? Yeah, this is normal. A squared plus B squared equals C squared. Yay! So this is your usual version of the Pythagorean theorem. Now, same is of course true down here on the vertical one. A is the distance from center to vertex. So B is always going to be from vertex to asymptote. And C is going to be the diagonal. Or C is the distance out to the focus. Same distance either way. I'm going to tell you the formula of a hyperbola. What's different on it than an ellipse? So there's not much. It looks almost identical to an ellipse. And he says it's subtracted. See the minus here? Ellipses had a plus sign between them. Hyperbolas are subtracted. Remember that definition said the set of points whose difference in the distances is constant. So hyperbolas have a subtraction sign in them. Otherwise, the formula is identical in that respect. Now the question is A always the larger number? Because on the ellipse, A was the larger number. So let us go play a moment. This one. I'm going to get the center off 0, 0. So, okay, I've changed the center so that you don't think the center has any impact on it. I moved the center somewhere. Okay, here's a hyperbola. This hyperbola is drawn where A is 2. You'll notice it says A is 2, B is 3. So therefore, is A always larger? Nope. In this case, B is. Am I allowed, though, to switch it? If I move A up there, now A is larger. It's 6.2, B is 3. Very close. A is always under the positive term. A is always the first one. B is always the second one. Doesn't matter which one's bigger or smaller. A is always the first one, B is always the second. Every single time. Move that 2. Now, what you're going to need to know when you go to graph it, watch those asymptotes. Here I had A really big, which is really pushing it out. As I make A smaller, in fact, now I'm to the point A is smaller than B, those asymptotes, the slopes of the asymptotes are changing. So we're going to be very concerned about what is the slope of those asymptotes? How slanted are they? So we will, actually you'll use that to draw your graph and be the slopes of the asymptotes. So that's probably a question we better figure out. In this case, how would I figure out the slope of those dotted lines? How does one find slope? What's the definition of slope from the very beginning of Algebra 1? Rise over run. Okay, looking here at our picture, you have a rise and a run in this picture. You went from the center up here to where B and C meet. How much did you rise and how much did you run? Yeah, I rose B, didn't I? And I ran A. So if you want the slope for the asymptote, you just need to do B over A. Now, why did I put a plus or minus on it? Yeah, because you got 2 asymptotes. You got one asymptote that's going positive. You got one asymptote coming down negative. So you got slopes You always have a plus or minus on them. Now, will it be the same when I look at this vertical one? It's rise over run, still B over A. Now down here on the second picture, I'm rising A, running B. So when you're doing a vertical one, the slopes are going to be A over B. But the bigger question is, how does the equation change when I'm doing a vertical one? Because if I come back to my picture, did this thing ever go vertical when I made A smaller than B? It's horizontal. When I made A bigger than B, it's still horizontal. How am I going to get the puppy to go vertical? Do it with the B. Bigger than A? Okay. If I make it bigger, B is now bigger than A. Did it make it go vertical? If I make it smaller than A, switch the signs of X and Y. What do you think? You're on the right track. Okay. That's what they said last month. Press the button that says vertical. Can you tell what changed? The Y is now first. The Y is positive and you're subtracting the X. So if you're doing hyperbolas, horizontal and verticals, whether X is first or Y is first. A and B don't impact the horizontal and vertical. A and B only impact, how wide my asymptotes gets, which how wide my curve gets. So an equation on a vertical one, you'll have Y first, but it will have A under it. A is always under the first term, the positive one. Okay. Other things they'll ask you to find, just like last time, they'll ask you to locate where the foci are. This is identical, the exact same as ellipses. You take the center. If it's horizontal, to get to each focus, you're going to have to move horizontally, so you're going to add it to the x-coordinate. You're going to add C. If it's vertical, you need to go up and down, so you're going to add C to the y-coordinate. However, there's one other thing they like to know on hyperbolas. They also want to know where the vertices are located. Where is the actual vertex on those bended curves? Which letter tells us where the vertex is? C is center to focus. A is center to vertex. So if A is center to vertex, that tells you how far over to the vertex. We guessed them all. So you're going to add A on instead of C. And if it's a vertical one, if it's going up and down, you add it to the y-coordinate instead of the x-coordinate. We needed to note this. Okay, so now that we've done all that, do you understand why you have a card? Yeah, too much info.